And in this lesson, we're going to focus on a specific phenomenon of sound waves known as the Doppler shift, which is caused by the relative motion of both the source of a sound wave and the observer. In order to really understand the Doppler shift, we need to understand really three different types of things, and kind of the terms are shown here. Spherical waves, which we've talked about before when talking about intensity, plane waves, and then wave fronts. All of these are going to help to kind of set up and understand the Doppler shift. Okay, so we already talked about a spherical wave. A spherical wave, basically they're waves emitted from a source that basically are emitted in all directions. If you remember, if this was the source, okay, they're going to emit out radially in all directions, okay, in all three dimensions. So if we were to create basically a circle or a sphere of sound waves, they're going to go out in any direction possible, okay. So this would be a spherical wave. Notice here that the spherical waves, the sound source is going to be oscillating, creating that sound wave, that disturbance, right? And basically what it's doing, if you think mathematically, it's forming concentric circles. These concentric circles are spreading out, continually spreading out in a certain direction. All right, what we call, when we look closely at these spherical waves, each concentric circle forms what's called a wave front, right? And that wave front travels with a speed v that's equal to the frequency of that wave times the wavelength. The wavelength is seen as the distance between the concentric circles. The frequency obviously is determined by the source, and really, like if you think about the wave speed we've talked about, wave speed really depends on the medium. All right. Kind of the rays that are shown here too, they're basically the radial lines that are coming from the source, and they're perpendicular to the wave fronts. All right, kind of the important thing about wave fronts and how it's going to affect the Doppler effect or Doppler shift is that wave fronts never intersect or overlap each other. Meaning that the source is always going to emit that sound, and these wave fronts, these concentric circles, will never overlap. Meaning this one here, call this wavefront A and wavefront B. Wavefront A will never overlap wavefront B. Okay, to say that, then this sound wave would be traveling faster than this sound wave, and if they're traveling in the same medium, that's just not possible. Okay, so these wavefronts will never overlap each other. Looking closer, when we look at the wavefronts, if we were to zoom in and if we were to move far away from the source, what happens to these wavefronts is the concentric circles begin to spread out, and these concentric circles start to become or look similar to, at a very close level, parallel lines. All right? So the plane, we call these then plane waves. Okay, a plane is just something in mathematics. Think of like a piece of paper that would be represented as a plane, like the X, Y, Z plane, those things. Okay, basically just parallel lines, and then these rays are seen to be parallel lines that are perpendicular to these wavefronts. Okay, so these wavefronts are seen as plane waves. They're moving all parallel to each other. All right, now what this then looks like is if we look at kind of far away from the source, spherical waves then become these plane waves. And notice the plane waves are separated by a distance of the wavelength. All right, the frequency is depending on the source. Again, the speed v is calculated by the frequency times the wavelength, and like I said before, that speed is going to be constant. Now, why is this important? Well, these plane waves are going to help us to understand the Doppler effect. The Doppler effect is now, instead of a stationary source, now we're going to have a source that is moving towards or away from these plane waves. Okay, so it's going to emit sound. These sound waves are going to travel at some speed, right? And the source is also going to be moving. Or we could also have some observer, right? And that observer could be moving towards or away from the plane waves, okay? So the Doppler effect is basically, because there's motion between the source or the observer, there's going to be a kind of a change in these plane waves. We'll look at that more specifically here. All right, so the Doppler shift, like I just said, it occurs when there is relative motion between the source of sound and the observer. All right, and what results is a change in frequency perceived by the sound. So a great example of this would be something like NASCAR. I don't know if any of you guys have seen NASCAR. All right, but say, here's our NASCAR track, and here are our stands. as the cars go around the track, right, they're kind of faint. But now as the cars are approaching kind of the fans right here, all of a sudden you hear a change in the pitch or change in the frequency of sound. And also what you find is you get a change in the intensity of the sound. And we'll talk more about why that is. All right? Sound is being emitted by the engine of that car, and you're getting a change in the frequency and change in intensity. Well, let's kind of think about what this really is due to. We said it's due to the relative motion. Okay, now relative motion is something we briefly talked about early in the year. All right, now what relative motion is think of a good example would be like on the freeway. Okay, say you're in a car and you're driving at 60 miles per hour, okay, to the right. All right, and if you look and cross the highway onto oncoming traffic and they're traveling 60 miles per hour to the left, if you, from your perspective, when you view this car here, the car does not seem to go 60 miles per hour, but this car seems to go a lot faster. You almost appear to be stationary while this car is moving at you with a greater speed. Well, its speed is dependent on the motion of the source and the observer, of the viewer and the other person, right? And really, what you would see is you'd get a relative velocity that would look kind of miles per hour, would look actually double of what you have. If you're both traveling at the same speed, that car is going to be appearing to go 120 miles per hour. Same can be said if you're traveling again at 60 miles per hour and a car is coming past you moving at 65 miles per hour. All right? Again, with this case here, right, it seemed like this car was going faster. In this case, you will see this car kind of inch past you, and this car will appear to be moving at a speed of 5 miles per hour. Right? So, same thing is going on with the Doppler shift. What's happening is you get a source that's emitting sound, and that'll be my emitting sound, that's going to be moving, and you can have an observer. So here's the source, that's the observer. The observer could be stationary, could be moving towards, could be moving away. Same with the sound. The sound could be moving, the source, could be moving towards, could be moving away as well, right? So the Doppler shift is really a change in that. And what happens is that we get these plane waves that we just talked about. Now, yes, it's concentric circles, but I'll show them as plane waves. And what happens is that as the source moves towards the observer at a certain speed, all right, the source is kind of catching up to these sound waves, right, that's already been emitted, and sound waves can travel at a speed that's relative to the medium. So what happens is you get the sound waves now that begin to stack on top of each other. And notice the difference from here to here. Okay, these are spread out, and these start to stack on top, and you get a change in the frequency. I also said it's caused a change in the intensity as well. What happens is that if you think of this, sound waves are energy, and what's happening is you're getting more energy in a given area, and that's going to change the intensity of that sound. Okay, so the Doppler shift changes both the frequency and the intensity of sound. All right, now how we calculate the Doppler shift, and I kind of put all these things together. If you look at your textbook, they give you multiple equations, and this is kind of my form of the equation, something that may be a little bit different than what you'll see in the textbook. All right, but it kind of puts it all together. So it says that the frequency, the observed frequency, is equal to the initial frequency times this factor here. Now this factor really is showing the relative velocity of both the sound, the observer, and the source. Okay, so V here is equal to the speed of sound. All right, and what does the speed of sound depend on? The speed of sound depends on, again, the medium through which it's traveling through. All right, so that speed's always going to be constant, and the majority of the time this speed is going to be around 345 meters per second. It's kind of the room temperature speed of sound. All right, this speed is constant, right? So with changing the speed of both the observer and the source, like we saw in the previous slide, is that you're going to get those plane waves that are going to begin to stack on top of each other. Okay, so notice here in the equation I give the plus or minus on the numerator and the minus or plus. Okay, these signs are basically showing relative velocities compared to the sound, the speed of sound. Okay, so we're looking at how does the speed of sound compare with the speed of the observer, and how does the speed of sound compare with the speed of the source. All right, so here's kind of how these signs go. For the observer, when you have a positive V0, when it's positive, the observer is moving towards the source of the sound. Okay, and when it's negative, the observer is moving away from the source of the sound. Okay, and that should hopefully make sense to you. Think mathematically, all right, if you're moving towards a sound, you're going to get that increase in frequency. All right, so that if you think mathematically, V plus V0 would give you a bigger numerator, which would then be multiplying V0 by a larger factor. Okay, think mathematically, hopefully it will make sense. Now with the source, it's a little different. It's kind of backwards. And to help you think about this, we'll think mathematically. Okay, when the source is moving towards the observer, what happens is that you place the minus here. So this would be moving towards. Now again, this is kind of going off of relative velocity, which I won't spend a lot of time on. But think mathematically. If the source is moving towards the observer, you're going to get an increase in the frequency, right? You're going to increase that observed frequency. So what's going to happen mathematically, if you have a minus here, okay, V minus Vs will give you a smaller number. And a smaller number in the denominator will produce a greater factor in which you're multiplying V0, or F0, I'm sorry. Okay, so the minus is just really can be shown mathematically, and hopefully that makes sense to you. The minus will create a smaller denominator, which will then make a larger factor, which will then give you a larger observed frequency. All right, and then opposite to that then, positive Vs would represent moving away. And again, think mathematically, V plus Vs, that will give you a larger denominator, which would make this factor smaller, which would make the observed frequency smaller. And if the source is moving away from you or from the observer, you should be getting a smaller frequency. All right. And I guess the other thing I kind of skipped over here is that F0 is not representing the frequency of the observer, but it's representing the original frequency of the sound being emitted. Okay, so Doppler shift is kind of a special case of the speed of sound, basically on the relative motion of the observer and the source. Right, but it kind of ties in a lot of things that we've been learning to this point. Alright, so let's do an example of the Doppler shift. So in this example, called a noisy siren, you have an ambulance traveling down a highway at a speed of 33.5 meters per second. The siren's emitting sound at a frequency of 400 hertz. What frequency is heard, some bad English there, heard by a passenger in a car traveling at 55 miles per hour, 24.6 meters per second? In the opposite direction is a car and ambulance, and now there's going to be multiple parts of this problem. So first one we're going to look as the ambulance and car approach each other. Okay. Second part we'll look at as they pass by and move away from each other. Okay. So the first one, here's the source. Source is moving, let's say, to the right. The car will be moving to the left. As they pass by, then you have, I'll show us the car is moving to the right, to the left, and the ambulance would be moving then to the right. And we're going to take the speed again. Majority not, if it's not shown, you can assume the speed of sound to be at that room temperature of 345 meters per second. And then the last one we'll do is what if they are traveling in the same direction, meaning if this is the ambulance, the car is moving in the same direction as the ambulance. So really this problem is looking at the many different cases you can look at. Okay, so let's start here by looking at part A. Okay, so part A is asking, what is the change in frequency going to be if they approach each other? All right, so kind of the picture is drawn here. So the equation we have, the frequency is V plus or minus VO divided by V minus or plus Vs times the original frequency. So V represents the speed of sound, so that's 345 in both the numerator and denominator. Now, okay, the ambulance here is shown moving to the right, the car is moving to the left, so they are both approaching each other. Okay, so if you think about the signs, the observer is approaching the source. So we would, in the numerator, add its speed of, in this case, 24.6 meters per second. So don't mind the units, okay, running out of space. And then in the denominator you have 345 meters per second. And since the ambulance is moving towards, here's the tricky part, this would be a minus. In this case, 33.5 meters per second. Again, mathematically, the numerator will get larger, denominator will get smaller. That's going to produce a larger factor, which is going to help increase the frequency. And then our original frequency is 400 hertz. Plug it into your calculator, and you get an observed frequency of 475 hertz. Okay, so notice again they're moving towards each other. The frequency of that sound wave is increasing. Alright, I'm going to move on to the next slide, and I'll do the kind of next two problems on that one, so make sure you write this problem down if you need. Alright, the next part of this problem is looking at when the ambulance and the car have now passed each other. So here's the car, here's the ambulance. Now they're moving past each other and they're moving away. Okay, so again we're using the same equation. So we got 345 as my speed of sound. Now let's think, okay, so our observer is the car, okay, and the car is moving away from the source, so that's going to be a negative 24.6 meters per second. Again, forget the units. And then you have 345, and the source is moving away from the observer, so that's going to be, and here's the trick, plus 33.5 meters per second times our frequency of 400 hertz. It's going to give us an observed frequency, oops, not F0, but it's going to give us a frequency here of 339 hertz. Okay, so again, think mathematically. Here the numerator is getting smaller, the denominator is getting larger. That creates a smaller observed frequency, and if the two source and observer are moving away from each other, that's going to create a smaller observed frequency. Okay, then the last one is now what if they're both moving in the same direction? Okay, so here's the ambulance, here's the car. Alright, so the frequency here is again 345. Since the car is moving away from the observer, that'd be minus 24.6 divided by 345. And since the ambulance is moving towards the observer, so source moving towards the observer, that'd be minus 33.5. So both minus in this case, times 400 hertz. Looking at the answer then, we will get 411 hertz. Notice in this case here that when they are moving away from each other, well, it really depends. How do you know if it's going to be a higher frequency or lower frequency? And that again depends on the relative velocity of the two, the source and the observer. In this case, the source is moving at 33.5, the observer is moving at 24.6. The relative velocity between those two, if you think, would be about 9 meters per second. Okay, so there's going to be this one, the ambulance is moving a little bit faster, therefore there's going to be a higher observed frequency by the car. Okay, so problems with dealing with the Doppler shift are going to be solved as that. Alright, now there's kind of some special cases of the Doppler shift that I'll quickly go through. Obviously the speed of the source can vary, and if you think about the speed of sound, especially in air, is a speed of 345 meters per second, which is a very fast speed. However, we do have the technologies nowadays to get at or above that speed of 345 meters per second. Okay, so there are some certain things that can happen. So one thing is you can create what's called a bow wave, and a bow wave is when the speed of the source is equal to the speed of the sound. Okay, so what happens is that as the source is moving, it's emitting sound, right, and that sound is basically just sitting right in front of it. Right, it creates these concentric circles like that, okay, where the sound and the source are moving at the same speed. And then the last one are shock waves, when the speed of the source exceeds the speed of the sound. So here's the source basically what's going to happen is it's going to shoot out sound waves, okay, but the source is going to be moving behind. So it's almost like, excuse the analogy, but it's almost like the source is kind of pooping out those sound waves, okay, and they're kind of floating behind them there, all right? And the larger those circles is representing earlier sound waves. So what's going to happen is you're going to get these sound waves that are going to stack on top of each other. So let's kind of look at this case of shock waves. So what happens when a shock wave is, like, obviously the source shown here is traveling faster than the speed of sound. All right. So you get kind of a diagram when looking at the spherical waves. You get this kind of diagram here, where you see that every time it emits a sound, the sound is going to propagate outwards from that location of where it's emitted, right? So it's emitted there, sound waves emitted there, emitted there, emitted there, emitted there. And notice that some of the sound waves are going to start to pile up on top of each other. And actually the sound waves are going to interfere with each other, which is something we'll talk about in the next lesson. Okay? So you get kind of these circles. If you notice at the previous diagram, if we draw a tangent line from the source all the way back to the initial sound wave, what happens is you get kind of a cone shape, right? And that cone shape kind of represents the shape of the shock wave, all right? And if you look, if we draw another line that goes from the source directly through where all, kind of the straight line path through where all the sound waves were emitted, all right? What happens, you see, is you get an angle between, you know, kind of draw a picture of it. Right here, kind of the circles. Okay, not the best drawing. And here's kind of that line I was talking about. So here represents the tangent line, and then here represents that other line. Notice that there forms, change the color, forms an angle between, you know, this line and the tangent line. All right, and that angle is equivalent to the speed of the source divided by the speed of the sound. Okay, V represents here the speed of the sound. Vs represents the speed of the source. Okay, when we look at the ratio of the speed of the sound divided by the speed of the source, this is what gives us basically a number. The units cancel out, so it's a unitless number, and this is known as the Mach number, something you've probably heard before. Okay, so that's kind of an interesting fact. And this cone shape, like I said before, this is what's called a shock wave. And then finally, here's kind of a picture of kind of a good representation of how a shock wave would look. Here is kind of a jet airplane that flew through some fog at basically traveling faster than the sound its engine was emitting. Right, and notice here you get kind of this conical shape around the plane that formed due to that shock wave. So kind of an interesting little application of the Doppler effect.